What the heck is going on here? What are these numbers doing together? Who arranged this playdate? I'll tell you who. It was a fella named James Stirling. He was born in the year 1692 in a lovely place named Stirlingshire. It is he who brought these numbers together, and indeed it is James Stirling who brings us together today to discuss these numbers. Like every great combinatorial story, it begins with balls and boxes. And so I ask you, humble viewer, how many ways can we put n distinct balls into k boxes? For an example, let's consider the case where n equals 3, so we have 3 balls, and k equals 2, we have 2 boxes. To make our 3 balls distinct, it's convenient to number them. As the question says, the balls are distinct, but the 2 boxes are not. This means, for example, putting balls 1 and 2 in this box, and 3 in this box, is the same as putting balls 1 and 2 in this box and 3 in this box. The particular box they're in doesn't matter, it just matters how they've been split up among the boxes. With that said, it's pretty easy to count the number of ways to put 3 distinct balls into 2 boxes. We could have ball 1 in its own box and balls 2 and 3 together in the other box. Alternatively, we could have balls 1 and 2, a cozy pair, together in their own box, and ball 3 all by its lonesome in the second box. The only pair of balls yet to commingle are balls 1 and 3, and so that's our last possibility, is putting balls 1 and 3 in their own box, and putting ball number 2 alone in its own box. So for n equals 3 balls and k equals 2 boxes, we see there are 1, 2, 3 ways the balls can be arranged among the boxes. Apologies for how small I wrote some of those numbers, those are supposed to be 3s. It's easy to see that to abstract this problem a little bit, instead of considering n distinct balls, we should just consider the numbers 1 through n. That's certainly convenient. And the boxes that we put them into are sets. In this context, they're often referred to as blocks. Like here, 1 is in its own block, and 2 and 3 are in their own block. We're now ready to see the glorious thing that James Stirling introduced. They're called Stirling numbers of the second kind. And what we've just discussed are partitions of numbers into blocks, just with less formal language. Indeed, the Stirling number of the second kind, written like this, is the number of ways to partition the first n positive integers into k blocks. A few remarks are in order before we look at some introductory examples. And if you want to see all the cool things we'll be getting to, or skip around, just check the video chapters. The first remark is to make sure this notation is clear. The letter n inside of these square brackets, this is just, as I said earlier, the set of the first n positive integers. So the set containing 1, 2, 3, and so on, all the way up through n. When we say n distinct balls, the formal way to represent that is like this, the set of the first n positive integers. You may also notice the similarity that this notation has to the notation for binomial coefficients. And indeed, the parallels with binomial coefficients will not end with the notation, as we'll see in this video. This notation for Stirling numbers of the second kind is read n subset k. Both the look of the notation and the way it's read ties back directly to the definition of the numbers. While we're using the word blocks here, we could also regard these blocks as subsets of this set. So this is the number of ways we can partition the first n positive integers into k subsets. So it's read n subset k. Whether we call them subsets, blocks, or boxes, it's all the same. This notation for Stirling numbers of the second kind isn't universal, but it is intuitive and it is lovely. And finally, this definition certainly begs one question in particular, which is what happened to Stirling numbers of the first kind? Well, when Stirling introduced these numbers, it was the numbers of the first kind which came second, and we will follow in his stead in that regard and say that Stirling numbers of the first kind That's a story for another day. With all the preliminary hullabaloo out of the way, let's look at some basic examples. Firstly, what are the values of n subset k if n is less than k? Remember the definition. This is the number of ways that n objects can be split up into k blocks. So if we don't even have k objects, we have n that's less than k, we don't even have k objects, it's not possible to split them into k blocks because it is assumed the blocks are non-empty. Let's make sure we're clear about that. The k blocks are non-empty. So in this case, we say that the Stirling number here is equal to 0. There are no ways to partition n objects, or the first n positive integers, into k non-empty blocks. On the other hand, if n happens to equal k, then there's exactly one way it can be done, which is to put one object, or one integer, in each of the n equals k boxes. So in this case, n subset k is equal to 1. In fact, n subset k is also equal to 1 any time that k is equal to 1. This should be pretty easy to see because if we're partitioning n distinct objects into a single box, well, the only option is to put everything in the one box. So in this case, the Stirling number is again just 1. Though, allow me to clarify, these equalities only hold as long as n is at least 1. If k is 1 and n is 0, well then we're in this situation where the Stirling number is 0. And if n and k are both equal to 0, then if you've done any combinatorics, you can probably guess we define this to be equal to 1. There's one way to partition 0 objects into 0 boxes, which is to do nothing at all. But when n is at least 1, we have these two equalities, and when n is at least 2, there's also one other basic equality we can state. If n is at least 2, then it's very easy to find the value of the Stirling number when k is 1 less than n. So n subset n minus 1, as long as n is at least 2, this is equal to the binomial coefficient n choose 2. This is because the only way to partition n objects into n-1 blocks is to pick 2 objects to be in the same box. That would then leave n-2 objects left and n-2 boxes left that need an object in them. So each of the n-2 objects has to go into one of those n-2 boxes, and all of those objects would be alone in those boxes. So there would be n-2 singleton blocks that have just a single thing inside of them, and one block with 2 things. So how many ways can this be done? Well, it's n choose 2. This is the number of ways we can pick 2 objects from n objects to be together in a box. Once 2 objects are placed in a box together, the rest of the partition is forced, because remember, we're requiring that there are n-1 non-empty boxes. Alright then, let us look at an example that is a bit less trivial. Consider 4 subset 2, the number of ways to partition 4 distinct objects into 2 blocks. This isn't covered by any of the identities we went over, so at this point, the best we could do is count them manually. A nice aesthetically pleasing way to do that is with a 4-sided shape. Indeed, with each square, we can let the 4 corners represent the 4 distinct objects, and we can use a highlighter to indicate the partition represented in each picture. For example, there are 4 partitions where each of the 4 distinct objects are by themselves in a block. So in this partition, that object is by itself, and then these 3 are together. In this partition, that object in the top right is by itself, and these 3 are together. Similarly with this partition, and with this one. The only other possibility are the partitions where 2 objects are together, like this one, and one other. Pictorially, the last partition is the one that looks like that. We thus see that 4 subset 2 is equal to 7. There are 7 ways to partition 4 distinct objects into 2 boxes. In fact, any Stirling number of the second kind with k equal to 2 is pretty easy to calculate. Because think about it like this. We're counting the number of ways we can split n objects among 2 boxes. Certainly, the first object has to go into one of the boxes, and that leaves n-1 objects left. For each of those n-1 objects, we then have two choices. Put it in that box with the first object, or don't. That's thus 2 to the n-1 possibilities, except for one which we need to subtract. The one possibility we need to exclude is where the answer to the question is yes for all n-1 objects. We say yes, put it in that box with the first object. We can't say yes for all of them, because if we did that, all objects would be in a single box. We can't have that. We need 2 non-empty boxes. And this formula is good for n at least 1. Plugging in n equals 4, we would get 2 to the power of 3, which is 8 minus 1, confirming the 7 we found before. Now you may be thinking, wow, this has been a whole lot of hogwash, a whole lot of beating around the bush. What about a general formula? And to that I say, hold your washed hogs. We still have a lot of interesting stuff to go over. Plus the general formula is a little bit of a big fat mess. We can't cover Stirling numbers of the second kind without going over this classic recurrence relation for calculating them. To calculate n subset k, we can actually look at n-1 subset k-1 and add k times n-1 subset k. Let's prove it. To prove this is true, we'll use a technique that's often useful, which is to focus our attention on a single element, just like we did briefly in explaining this formula. So regarding this as counting partitions of the first n positive integers into k blocks, let's focus on 1, and first, suppose that 1 is a block all on its own, so 1 is by itself in a block. If 1 is all by itself in a block, well then we have n-1 numbers left, 1 through n, and we have k-1 blocks remaining that must get stuff inside of them. That's where this comes from. In the case where 1 is in a block all by itself, the possibilities are enumerated by n-1 subset k-1. The other possibility is that 1 is in a block with other numbers. Maybe it's in a block with a single other number, maybe multiple other numbers. Point is, though, it's not by itself. In this case, think about those n-1 other numbers, those numbers besides 1. All we need to do is think about how many ways they can be partitioned into k blocks, because 1 is in one of the blocks, but those numbers can go in that block with 1, because we're not restricting 1 to be by itself. So the idea is, well, let's count the number of ways that we can put those n-1 other numbers into these k blocks. And once those numbers other than 1 are put into the k blocks, this then needs to get multiplied by k, because any of those k blocks could be the block that has 1 in it. So this counts the number of partitions where 1 is not by itself. By counting the partitions where 1 is by itself and where 1 isn't by itself, we can of course add them up to get the total number of partitions and prove this recurrence relation. And those of you well acquainted with binomial coefficients probably recognize this as exactly the type of recurrence relation to lead to one of those classic combinatorial triangles. We thus obtain Stirling's triangle. I've written out the first few rows of the triangle. Note that as the rows go down, n increases. N equals 0, n equals 1, n equals 2, and so on. As we go across the rows, k increases. K equals 0, k equals 1. K equals 0, 1, 2. Each row always starts with 0, except for the first one, because there's no way to put a positive number of objects into 0 boxes. Then to get the next number, we just add the two numbers above it, except the second one needs to get multiplied by k. Here, k equals 1, so this would be 0 plus 1 plus 1, so 1. For the next number, again, add the two numbers above it, except the number on the right needs to get multiplied by k. Now, k is 2, so 1 plus 2 times 1, so 3. And then at the end of the row, where n equals k, we have 1. Ignore this incorrect triangle I had to cross out. You can see how the recurrence relation describes this. This is the above number to the left, and then this is the above number to the right, except multiplied by k. So 1 plus 2 gives us that 3. Let's do one more row. It starts with 0, then 0 plus 1 times 1, which is 1, then 1 plus 2 times 3, which is 7, then 3 plus 3 times 1, which is 6, and then 1. Quickly, let's just do one more row. 0, 1, 1 plus 2 times 7 is 15, 7 plus 3 times 6 is 25, 6 plus 4 times 1 is 10, with a 1 at the end. And now, who brought these numbers together for a playdate? Well, we walk in the shoes of the master. There is a small variation on this problem, which is actually quite important for us to discuss. And that is, how do we count the partitions if the blocks or boxes are distinct? This is actually quite an easy question to answer. We start with the Stirling number of the second kind, n subset k. This tells us how many ways we can partition n objects into k blocks. But then how do we account for the fact that the blocks are meaningfully different? 1 and 2 going into block A is different from 1 and 2 going into block B. Well, since there are k blocks, all we have to do to account for this is to multiply by k factorial. Since the blocks are distinct, we can just regard all k of them as having a label 1 through k, and so then multiplying by k factorial just accounts for all the different ways they could be labeled. Now, there's actually something quite interesting about this, which is that it counts the number of surjections from the set of the first n positive integers to the set of the first k positive integers. For example, particularly if you don't know what a surjection is, consider n equals 3, so we have this domain with the numbers 1 through 3, and k equals 2, so we have this codomain with the numbers 1 and 2. A surjection is a function that covers the codomain, which means every element here, 1 and 2, will get mapped to by something in the domain. So an example of a surjection would be this function that sends 1 to 1, 2 to 1, and 3 to 2. On the other hand, it wouldn't be a surjection if 1, 2, and 3 were all sent to 2, because then nothing is getting sent to 1, so the codomain is not being covered. So then, why the heck does this count surjections from the first n positive integers to the first k? It's because mapping these n positive integers into k positive integers is like splitting up these n positive integers among k blocks, except the k blocks, in this case it was 2 blocks, those k blocks are distinct, they're different numbers, so this is the formula that counts that number of surjections. For example, this surjection is like 1 and 2 being together in a block, and 3 being in its own block. But in this case, the blocks are labeled because they are elements of the codomain, so a different way a similar situation could occur is if 1 and 2 were both going to 2, but 3 was going to 1. That's a distinct surjection, and hopefully you can see then the connection with this expression. N subset k counts the ways that n objects could be split among k blocks, and then multiplying by k factorial accounts for the different ways those blocks could be labeled. This is going to be directly relevant to our argument for the formula for Stirling numbers of the second kind, so don't forget it. But first, let's look at one other interesting place these Stirling numbers pop up. There is not much reason at first glance to believe that this should have anything to do with Stirling numbers, let alone of the second kind, so in me, you'll have to place your faith. Say k and n are positive integers, with both of them at least 1, and n is at least k. Then, let h of nk be the sum of all n-k factor products with all of the factors in the set of the first k positive integers. A factor in a particular product is allowed to repeat, however, we should write the factors in increasing order, so 1 times 2 and 2 times 1 wouldn't both occur in a sum. So when we say this is the sum of all products, we mean up to ordering. We're not considering the different ways a product could be ordered, because order of multiplication doesn't matter. There's a good chance, though, that you're still wondering what the heck I mean by this, so let's look at an example. Let us consider, for example, h of 4, 2. Notice that 4 minus 2 equals 2. That's n minus k in this description. This means that this is going to be the sum of all products that consist of 2 factors, n minus k here is 2, where those factors are from the set of the first two positive integers. So notice how the 4 here is really only telling us how many factors the products are allowed to have. 4 is 2 more than 2, so each product can have 2 factors. If this was a 5, then each product could have 3 factors, but still they would have to come from the set of the first 2 positive integers because k equals 2. So we'll take all possible products of this sort and add them up. That gives us the value of this function. The possibilities are 1 times 1, 1 times 2, and 2 times 2. Hence, the value of the function at 4, 2 is 7. Now, the wisest among you may immediately notice that this is the same as 4 subset 2. We evaluated this earlier and found it was equal to 7 as well, and this is no coincidence. Indeed, this peculiar function we've just introduced, h of nk, is in fact always equal to n subset k. Now, that's a pretty spooky claim, isn't it? But don't take my word for it. Let's prove it. The proof begins with the critical step of showing that this function satisfies the exact same recurrence relation that we previously showed the Stirling numbers satisfied, this one here. Written in terms of this h function, the recurrence relation appears like this. To show these two things are equal, as we claim, is a pretty straightforward exercise in counting. First, the item on the left is, by definition, the sum of all n-k factor products with factors in this set. To show that the sum on the right is in fact the same as this sum on the left, we will, similarly to before, consider our attention on a particular factor. First, let's consider the products which contain k as a factor. If one of the factors in a product is k, then there are n-k minus 1 other factors in the product, and they all come from the set of the first k positive integers. So again, since each product is an n-k factor product, a product that contains k has n-k minus 1 other factors, which of course are all from the set of the first k positive integers. And that's represented by this term here. Remember, the number of factors in a product is this argument of the function minus this argument. So the number of factors in products represented by this guy are n minus 1 minus k, or equivalently, n minus k minus 1. This h function takes all such products and adds them up. But we're trying to account for all of the products that have k as a factor. So you can imagine all of the terms in the sum represented by this function have that factor of k, except we've factored it out, and that's why there's a k out here. Thus, in total, this product, k times this h function, that is the sum of all products that contain k and n minus k total factors, where they are all from this set. On the other hand, it's easy to see how this term represents the sum of the products that do not contain k. The difference between the left argument and the right argument is still n minus k, so this is a sum of products that have n minus k factors. However, since k isn't in any of these products, the factors can't come from this set, they have to come from this set, the set of the first k minus 1 positive integers. Since this is the sum of all products without k as a factor, and this is the sum of all products with k as a factor, we have shown that the left side equals the right side. Now, with the knowledge that these two creatures satisfy the same recurrence relation, it will be an easy task to show that they are always equal. To that end, we're going to use a proof by induction, performing induction on the sum n plus k. Remember, the h function has two arguments, n and k. So by performing induction on their sum, we're able to account for n increasing by 1 and k increasing by 1. If either of these increase by 1, the sum will increase by 1. The basis step of most induction proofs is very routine and practically trivial. We do have to be a bit careful for this one though. Based on our definition of the function, the smallest n plus k could be is 2, when n and k take on their smallest allowed values of 1. In this case, this is a sum of 0 factor products because 1 minus 1 is 0, so the products can't have any factors, and an empty product, we know, is equal to 1, just like anything to the power of 0 is 1. And of course, this is equal to the Stirling number of the second kind, 1 subset 1. You'd probably like to stop the basis step here, having verified the first possible case. However, as you'll see in the induction step, we'll actually end up subtracting 2 from the sum n plus k, which means we're going to need to prove that our result is true up to n plus k equals 4. That way, when we subtract 2, the smallest possibility is that we've backed ourselves up to this situation, which we've already verified. But if we don't prove up through n plus k equals 4, then taking 2 away from n plus k could potentially put us in some bad territory. So let's verify the case where n plus k equals 3. The only way that could happen is where n is 2 and k is 1. Remember that n needs to be at least as big as k, so it's not possible that k is 2 and n is 1. This is equal to 1 because the only one factor product with all factors consisting of the first positive integer, that's just 1. And this is indeed equal to the Stirling number of the second kind, 2 subset 1. There's only one way to put two objects into a single box, which is to put the two objects in the box. And then finally, taking us to n plus k equals 4, we look at h of 2, 2, and again, this is equal to 1 because this is an empty product. And this is equal to the Stirling number of the second kind, 2 subset 2. There's only one way to put two objects in two blocks. Alright, with these small cases established, we are done with the basis step. We then move on to a pretty routine induction step. Our induction hypothesis is to assume that n subset k is equal to h of nk for all n plus k less than or equal to m. So this is actually strong induction. This is a valid assumption because we know this is true for m equals 4. We then, of course, will consider the next possible case where n plus k is equal to m plus 1. Of course, we don't really want to work with m plus 1, but we can immediately cut these arguments down by applying our known recurrence relation. Indeed, we know that n subset k is equal to n minus 1 subset k minus 1 plus k multiplied by n minus 1 subset k. Now, n plus k here equals m plus 1. But now, in this Stirling number of the second kind, we've reduced both arguments. We have n-1 and k-1. Their sum, then, is certainly less than or equal to m, and so our induction hypothesis applies. Namely, this is equal to h of n-1, k-1, and similarly for this term. Now that we've replaced the Stirling numbers with the h function, we can apply the recurrence relation which we proved for the h function. This is explicitly equal to h of nk. That's what we just proved earlier, and that completes the induction step of the proof. You can then drop a QED, a small square, or whatever is your favorite victorious iconography, but we have established that h of nk is equal to n subset k by the principle of mathematical induction. Now, having put that issue to bed, since it was interesting, I suppose it's time that we prove the general formula. I'm sure you're very excited to find a formula for n subset k, but we're actually going to find a formula for k factorial times n subset k first. This is just going to be helpful for our argument. Once we find the formula for that, of course, we can just divide everything by k factorial and finally have the formula we're looking for. Now, what's so important about k factorial times n subset k that we'd rather find a formula for that? Well, remember, this counts the number of surjections from the set of the first n positive integers to the set of the first k positive integers. So we need to come up with a formula for the number of surjections from here to here. It's easy enough to count the total number of functions from the set of the first n positive integers to the set of the first k. That is just k to the power of n, because each of the n elements in the domain have k choices of where to go in the codomain. Since there are k choices for n elements in the domain, the number of possible functions is k to the n. Of course, many of these functions will fail to hit some of the elements in the codomain, and thus will not be surjections. Some functions might never map to the element 1. Some may never map to 2. Some may may never map to 1, 2, or 3. So to count the number of surjections, we're going to count up all of those functions that miss elements of the codomain, and then take that number away from the total number of functions. So we're going to count up the non-surjections. For this, we'll need some new notation. Let AI be the set of functions from here to here that don't map to I. For example, the set A1 would contain all functions that don't map to 1. If one of those functions also doesn't map to 5, for example, that function would also be in A5. So many of these functions will belong to multiple A sets, which of course presents a challenge, because we need to count up the total number of functions in all of these sets AI, but since many functions will be in multiple sets, we have to be careful. For starters though, it's easy enough to count the number of functions that are in a particular set AI. In the set AI, we just have all functions that don't map to I. If a function doesn't map to I, well then every one of the n elements in the domain have k-1 choices of where to go. They can't map to I, but anything else is fine, so k-1 choices total. Thus, the total number of functions in each set AI is k-1 to the power of n, k-1 choices for all n elements of the domain. And we can go a step further and specify the number of functions that are in a j-fold intersection of these sets. Suppose we take a handful of them, AI1, AI2, all the way up through some AIJ, and intersect them. This would contain all functions that don't map to I1, and they don't map to I2, and so on, and they don't map to IJ. How many functions are there in such an intersection? Well, it's just like the logic from before, except instead of one excluded element, there are 1, 2, up through j total excluded elements. So the total number of functions in a j-fold intersection like this would be k minus the j forbidden elements to the power of n, k minus j choices for each of the n elements from the domain. And I may want to specify this about those indices I1 through IJ. They're all at least 1, that's the smallest number that could be excluded, and they're all less than or equal to k because that's the biggest number that could be excluded. Additionally, we may say that I1 is less than I2 and so on up through IJ. That way we've written them in increasing order, and we're saying that all of these indices are distinct. So this isn't AI1 intersect AI1, for example. There's no point in writing that. So we're requiring that all these indices are distinct, and so let's write them in increasing order. I point this out specifically because it's going to show up again in a minute. So then, the big question, how are we going to count up the total number of functions in all of these sets AI without double, triple, or quadruple counting any of the functions that appear in multiple sets? And again, remember right now we're trying to count the number of non-surjective functions, so we can subtract it from the total number of functions to thus obtain the number of surjections. Well, to do this tricky counting, we need to use what's called the Sieve theorem, or the inclusion-exclusion principle. It's critical that you understand that principle for this problem. I'll leave a link in the description to a more in-depth video where I discuss that, but just as a really quick intro, imagine there were only 3 sets, A1, A2, and A3. Here's what the principle looks like in that situation. We say, well, I want to count up all of the functions that are in A1 and A2 and A3, so I'm going to add their cardinalities, the number of elements in A1 plus the number of elements in A2 plus the number of elements in A3. I'm including all of these functions. The issue is some functions are going to be in 2 of these sets. Some functions miss 1 and they miss 2, so they're in these 2 sets. Some functions miss 2 and they miss 3, so they're in these 2 sets. And thus, functions like that we have double counted. Thus, we need to exclude or subtract the 2-fold intersections to correct that double counting. So we subtract the number of functions that are in A1 intersect A2, because those functions were counted in A1 and in A2. We don't want to double count them, so let's exclude them once. The same can be said about functions that are in A1 and A3. And excuse me for going over a line, the same must also be said about functions that are in A2 and A3. So we've now excluded all of those functions that were double counted. But there's still an issue, because some functions miss 1, and they miss 2, and they miss 3. A function like that would be counted 3 times here, but then it would be excluded 3 times. So we have to include it back into our count. Thus, after including what we would call the 1-fold intersections, then excluding the 2-fold intersections, we now have to include the 3-fold intersections. So add the number of functions in A1 intersect A2 intersect A3. To apply this principle in more generality, it requires some ugly summation symbols, so it's good to have a grasp on a smaller example. This is exactly what we have to do, just generalized. So then let's go through our application of the sieve, or inclusion-exclusion principle, to count the total number of functions that are in all of these A sets. So we're bringing all of the sets together with unions and counting the total number of functions in the union. Remember, in our problem, there are k elements which could be excluded because there are k elements in the codomain, so we have A1 up through AK. To find the number of functions in a union of sets like this, we use inclusion-exclusion. And let me write this just a little bit lower so that I have some ceiling room. And there it is. This is the application of the inclusion-exclusion principle to this particular scenario. Sorry, right here before the ellipses, I should have squeezed in an intersection symbol here just to indicate the operation taking place between all those sets. So notice out here, we have j starting at 1 and increasing up to k. And that's affecting these intersections here. When j equals 1, we're adding up all of the 1-fold intersections. That means we're just adding up the cardinalities of the individual sets. Then when j equals 2, this sum adds up all possible 2-fold intersections, then all possible 3-fold intersections, and so on. And note out here we have that -1 to the j minus 1. This is doing the including, then the excluding, then the including, and so on. When j equals 1, this is -1 to the 0, which is 1, so we're including stuff. But then it's going to be -1 when j equals 2, so then we're excluding, then we're including, then we're excluding, and so on. But now we're in luck, because remember that we actually know the cardinality of any given j-fold intersection of these sets. As we previously discussed, the number of functions in a j-fold intersection is just k minus j to the power of n. So every j-fold intersection has k minus j to the n elements. We just need to count how many j-fold intersections are possible at each step. And of course, the number of j-fold intersections that are possible at each step is k choose j, because there are k sets available, A1 through AK, and we're picking j of them, so k choose j. We're thus able to rewrite this sum in this much more compact form. Every j-fold intersection has a cardinality that's known. It's k minus j to the n. How many of them are there total? K choose j of them. Where still j ranges from 1 through k, and we have this -1 doing the including and the excluding. This then is the number of non-surjections, and what we have to do is subtract it from k to the n to find the number of surjective functions. So our lovely expression from before, which involves the Stirling numbers of the second kind, k factorial n subset k, which we know counts the number of surjections, this is equal to k to the power of n, the total number of functions, and then minus this, the number of non-surjections. Instead of subtracting this, though, that's the same as adding this, but just bringing a factor of -1 inside, thus just increase the power of -1 by 1, from j minus 1 to simply j. Now check this out. What would this term of the sum be if j were to equal 0? Well, this would be 1, k choose 0 would be 1, and k minus 0 is just k, so this would be k to the n. The whole term would just be k to the n, which is this. That means we can actually include this in the sum by just starting the index at 0. So then finally we have that this equals this, and now we just have to divide both sides by k factorial to get the Stirling number all by itself. Once we do that division, we get here. N subset k, the Stirling number of the second kind, is equal to 1 over k factorial multiplied by this sum. Now though, if you know your binomial coefficients, you know that this, k choose j, can be written with a k factorial in its numerator. It's k factorial divided by j factorial times k minus j factorial. So in fact, we might as well bring this 1 over k factorial inside the sum to cancel out that k factorial from the binomial coefficient. And we thus arrive at a form that's probably as good as we're gonna get it. -1 to the j times k minus j to the n divided by j factorial times k minus j factorial. That denominator is from what remains of the binomial coefficient. And so that's our beautiful formula for Stirling numbers of the second kind. It's not what's generally regarded as a closed form expression because of the summation, but at least it's not a recurrence relation. Well, I really hope you thought that was as fun and interesting as I did. If so, please consider supporting what I do by joining Wrath of Math as a channel member. You can get early and exclusive access to all sorts of videos and original music, lots of fun stuff. So let me know in the comments if you had any questions, and be sure to subscribe for more of the swankiest math videos on the internet.
I'm unstable, I'm feeling hard to keep the cable cut and untuck the cable. If Texas Instruments don't reply, well, I think this time it might be fatal. Wish to sell my own fake, cause I'm jaded.
Hate the odds that I calculated.
Press and pull and pray and push it all the way through the whole blue planet.
Planet faded.